So today we're going to be looking at the confidence interval for a population mean when you know the standard deviation. This is the second type of confidence interval question that we might come across. So last time we did population proportion, which is with a percentage. This time we're going to be looking at estimating a population mean, which is an average. So first question is, well, what's the difference between these two questions? Like, how do I know when I'm doing a proportion? How do I know when I'm doing an average? Well, remember, proportion questions talk about, as I keep saying, the percentage. So what percent of people think, have, do, etc. So when you ask what percent of people in the area blank blank, that's a proportion question. When you're asking what the average number of people in the area do blank are, or what the average something of people in the area is, that is a population mean question. So for example, the average IQ score of high schoolers in Champaign, Illinois. That'd be an average question or a mean question. Average height of women between 20 and 30 years old in the US. That's a mean question. Average number of pets owned, average number of people infected, that sort of thing. So those are all population mean questions. So again, use the wording of the question to denote what type of problem you're going to come across. So how do we actually get these confidence intervals for this type of question? Well, there's actually two different versions of this. One is when you know the standard deviation, and one is when you don't know the standard deviation. And we're going to focus on the case when you do know the standard deviation in this video. So if you don't remember, the standard deviation is this little fancy letter right here, this sigma, lowercase sigma. And what this basically tells you is how spread out your data is. It's a number that represents how diverse um, your population is. So like, for example, if I was just taking a list of numbers, let's say I just list out 1, 2, 1, 3, 3, 2, 1. These would have a very low deviation because all the numbers are pretty close together. They're all within kind of the same area. There's a 3 there. Whereas if I listed these numbers like 10, 1, 20, -5, 70, 1000, these would have a very high deviation because these numbers are very spread out. They're not really clustered together like the first set of numbers are. So deviation is simply a number that tells you how spread out your data is for your population. So if these are like the weights of people, this would be a very uh, low deviation of weights. This would be a very high deviation of weights. This would be a very low deviation of number of pets. This would be a very high deviation of number of pets, even though you can't have -5 pets. But so that's what deviation means. So if you know it, we're going to go through these steps in this video. If you don't know the standard deviation, there's another kind of path you have to take. But let's assume you do. So we're going off the assumption that we know the deviation of the population. We know how spread out the population is in terms of this item that we're measuring. Well, like always, we first need a point estimate because our point estimate is going to kind of form the middle or the basis of our interval. And last time we used p hat as our point estimate for a population proportion, right? We used p hat because we're estimating a percentage or a proportion. So we use the sample proportion to get our point estimate. Well, in this case, if we're trying to test the population mean, we're going to use the sample mean, which is usually denoted as x bar. That's what we call the sample mean. And again, this kind of makes sense because your best single numerical guess for the average of something is simply to say, well, let me take a bunch of people, find out what I'm trying to measure, average them up, and that will be my best guess. So, for example, if somebody asked you what the average weight of guys in your apartment complex is, the best guess you would have would be to take a sample of guys in your apartment complex, weigh them, find the average, and that'd be your best guess. Obviously, the more guys you have in that average, the more accurate your answer is. But that would be your best single estimate. Now, would it be a good estimate? Maybe, but again, single numerical estimates generally aren't used that often because we want a range of values because that's going to be more accurate and we have a bit more confidence in giving them an interval rather than giving them a single numerical answer. And once we have our point estimate, we have to have our margin of error. This is what actually makes our interval an interval, right? So usually it's the point estimate. So all our stuff follows this basic format here. Point estimate. I'm going to try my best to write as neatly as I can here. Point estimate, and it's plus or minus margin of error. All the confidence interval stuff we're doing for mean, for deviation, for proportion, everything we're doing here in this little section all boils down to this single format. point estimate plus or minus margin of error. Or you can, again, write the full interval with the less than signs and, have the low end here and the high end here if you want to. But it still boils down to the same thing. Point estimate plus or minus margin of error. And the margin of error is when the formula comes in. Now, for proportion, we had that square root p hat q hat over n times z sort of thing. For a population mean, we have this formula here. The population mean's margin of error is the critical value, so z is still the critical value, so CV, times the standard deviation, which again, we're assuming that we know, over the square root of n. It's actually a lot nicer than the other proportion formula, if you ask me. So let's run through an example here. 80 students were selected to figure out the length of time it took them to earn a bachelor's. Out of the 80 students, we found that the average length of time was 4.8 years. The deviation is 2.2 years for the entire population. So everybody in this population that we're studying here, let's say we're studying in a town or a city, everybody in that town or city, the deviation of getting a bachelor's degree is about plus or minus 2 years. And it's not a margin of error, but it's kind of talked about the same way. Construct a 95% confidence interval to estimate the average length of time to earn a bachelor's degree. Well, let's start listing out our numbers here. So we need our n, we need our z, we need our sigma, and that's about it. Because like I said, we have a lot less to actually need here. We also need our x bar to get our point estimate, but again, that's going to be given to us. So let's just run through this here and see what we can find. So 80 students were selected. Well, that's pretty clear that's an n there, right? We're going to select 80 students to survey. From the 80 students, they had an average time of 4.8. So average time of 4.8. So that means that this is my sample average. This is the average of the people that I'm surveying. So 4.8 here. And the population deviation is 2.2 years. Well, that's pretty clear. It says deviation right there. So population deviation is 2.2. And remember, our z is gotten from our listed critical values. So we're doing a 95% confidence interval. So my z-score is going to be, let's see here, make sure I get my table right. For a 95% confidence interval, we have a 1.96 critical value. And I'm just getting that from the z table, or again, you can look back at the previous videos and write down those critical values as well. And again, if you Google Z chart or Z table, you'll get a bunch of different types of tables, and most of them will have the 95, 90, and 99% confidence interval critical values listed as well. Or like I said, you can go back to the previous video on proportion intervals and copy them down from there. So let's go ahead and calculate my margin of error. So my margin of error is my critical value times my deviation all over the square root of my n. So let's go ahead and calculate this up here. I forgot to pop up my calculator beforehand. So we have 1.96 times 2.2 over the square root of 80. And we get 0.482. So 0.482. I'm usually okay with 2 decimal spots rounding, but I'm just going to do 3 here because I just feel like it. Usually 3 decimal spots is the standard, quote unquote, but when people ask me, I usually just say 2 just because it's a reflex. So 0.482 is my margin of error. So we have 2 ways of writing our answer, right? We have our point estimate. Remember this right here, x bar, that's our point estimate. That's where my estimate begins. That's the best single numerical estimate I can give. So my best single numerical estimate, 4.8, plus or minus 0.482. So 4.8 years plus or minus 0.482 years is my 95% confident guess, so to speak. If you want to make this into an interval, you'd have, now the number we use for average is, or the letter rather, is mu. This is the Greek letter that stands for average. So we wouldn't put a p in the middle because we're not estimating a proportion. We're putting a mu in the middle because we're estimating an average, just so that your person or statistician or whatever knows what the heck this number means here. So 4.8 minus 0.482 gives us 4.318. So whoops, let's try that again. 4.318. And then on the high end, we get 5.282. So we are 95% sure that the average length of time it takes somebody in this area to get a bachelor's degree is between 4.3 and 5.3 years, essentially, if you round off to one decimal spot. Or again, if you really want to round it high, you'd be between 4 and 5 years. But usually, like I said, 2 or 3 decimal spots is the standard rounding for this kind of stats. Again, it's just like the last one, except you have a different formula for E, and you're looking for different values. But the intent is the same. Get your point estimate, which in this case is your sample mean, get your margin of error, and then it's just plus or minus those. And one last thing here is that we've been using this margin of error a lot in both types of calculations. So this kind of begs the question, well, what if I don't know how many people to sample? What if I want my margin of error to be a certain number, and I want to sample people enough so that I can have that margin of error? Let's say you're running a survey and you want to be within plus or minus 2%. Well, how many people do you need to survey to be within plus or minus 2%? Or to be within plus or minus 5? Or let's say you're tracking IQ score and you want to be within plus or minus 10. How do I figure out how many people I need to survey to get a needed margin of error? Well, for average, we actually have a formula for that. We just kind of solve, if you take this formula here, E equals Z times sigma over square root n. All we do is we take this formula and solve it for n. So if you go back to algebra 1, multiply by square root of n, divide by e, square both sides, you get this result here. Again, you could do the same thing for a population proportion too. So remember, for population proportion, the margin of error was z times the square root of p hat q hat over n. Whoops, check back. P hat q hat over n. If you solve this for n, which is not untrivial, but it's actually not that bad either if you know your basic algebra 1s and squaring and square rooting. But if you solve this for n, you can figure out how to find how many people to survey if you want a certain margin of error for your population proportion questions. But for a population mean, this is how we get our n. And if you notice here, this has nothing to do with how big our sample is or how big our population is, which is kind of extravagant, to be honest. It's kind of awesome because this means that we don't need to know how many people are in a population. Let's say we want to survey some stuff about the United States. We don't need to know how many people are actually in the United States to get a targeted margin of error, because the margin of error is simply based on the critical value you want, the sigma that you know, so deviation that you know, and what the margin of error you want is. If you all know those three things, then you can get how many people you need to survey to get that needed margin of error. So if you want a margin of error of plus or minus 5 with a 95% confidence interval, as long as you know the sigma, then you don't need to know how many people are in the entire population to get how many people you need to survey. Now, this doesn't mean you can just pick, let's say you're doing a test and you want to figure out, okay, how many people in the United States have red hair? The average number of people in the United States that have red hair. And let's say you run this stuff and you get like n is equal to 100. And you say, okay, I need to survey 100 people to accurately figure out how many people in the United States have red hair within plus or minus 2. Let's say your margin of error target was 2. Let's say you want to be a really accurate survey. So you're saying, okay, I'm going to survey 100 people. I'm going to run my data. I'm going to be correct within plus or minus 2 for the average number of people in the United States that have red hair. And then you go ahead and you go to Champaign, Illinois, and you survey 100 people, and you run your data, and you say, aha, this is my answer. Well, that's not quite correct, because this 100, even though you need to survey 100 people, you still need to make sure that your survey is representative of the entire population as a whole. So you can't just pick 100 people from Champaign, Illinois, because you're not actually getting the diverse population of the United States. You want to make sure to get a sample of 100 people split among all the states as much as you can. States that have a higher population, you want to survey a little bit more. States that have a lower population, you want to survey a little bit less, just to make your sample representative in the entire United States. If you want to survey 100 people from just Champaign, Illinois, then your survey would be accurate for Champaign, Illinois. It wouldn't even necessarily be accurate for Illinois as a whole. So again, picking samples is not just a matter of reaching a certain number. It's a matter of making sure that your sample is a diverse enough representation of your population for it to be accurate. That's why, just to get a little current events here, that's why this whole case with this virus going on, when people give you stats and whatnot, it's always important that they're taking stats from the population as a whole, not from specific provinces or specific states or whatever, unless they're using their stats for that specific state. Like let's say they say the population of people who are infected is this number. Well, is that just for people in New York? Is that for people in the United States? Is that for people in the world? Again, when they throw stats, you always kind of ask yourself, well, where are we getting our sample from? Are we taking people just from this area, or even just from certain time frames? Are we surveying people just who come into the hospital? Let's say we're trying to figure out how many people might be infected in New York. Well, if we're taking our data just from people who come into the hospital asking to be tested, well, what kind of people are going to come into the hospital asking to be tested? People who think they have the virus. So that's going to be not necessarily an accurate representation of New York or any county as a whole, or any city rather as a whole, because you're only getting samples from people who think they might have, who have a predisposition to having the virus potentially. Whereas if you want a really accurate sample, you would go ahead and survey people at random, not just people who come into the hospital, because as they say, some of those viruses people might have it and not even know it. So again, always be careful with the stats that they throw of you, especially in these times. Just kind of second guess, or at least not second guess, but check and think about, okay, where they're getting the sample from. Is there any way this might be skewed one way or another? That sort of thing. So just to run a real quick example of this, now that I got off that tangent there, um, businesses do this too. So let's say an arcade is losing money because people are using fake quarters. So they get a piece of metal, they kind of shape it down to a quarter, and they kind of put it in the arcade machines, and the arcade machine thinks it's a real quarter and then lets them play when they shouldn't. So the arcade's going to go ahead and adjust the machines to narrow the limits on what it's going to accept as a weight for a quarter. This is to make it a little bit harder for the slugs to actually work, because an arcade machine is going to accept a weight within a certain range, and so the company wants to kind of narrow this range down so the slugs might not be as effective. So they want to figure out, okay, how many quarters do we need to weigh so that we can construct a 99% confidence interval that the sample mean is within plus or minus 0.025 grams of the actual weight. And assume that we know from the US Mint that the population deviation of quarters is within 0.068 as a deviation, which again is a very low deviation. So quarters are pretty uniformly the same weight because the deviation is pretty low. But again, we're dealing with arcade machines here. We might need some fine tuning, because a little bit more, a little bit less weight is going to trip the machine either yes or no. So this low deviation here is very necessary. So we want to figure out how many quarters do we need to average, how many quarters do we need to survey, so that we are 99% confident that our machine is going to work within plus or minus 0.025 grams of the quarter. So if it's 0.05 grams more or 0.05 grams less, the machine won't accept it. We want to make sure that our machine is only within 0.025 grams, not anymore. So that's our margin of error that we want. That's the give that we're going to let the machine operate between. Well, how many quarters do we need to survey? Well, first off, we need to know our z. Well, if we're doing a 99% interval, our z is going to be it's not 2.575. What is our population deviation? Well, it says here that's 0.068. And what is our desired margin of error? Well, that's going to be plus or minus 0.025. We normally just use the positive version just because we can just slap a negative on it at the end and make it negative if we need to. And then we're going to calculate. So we're going to go back to our formula here. N is equal to, and again, this is just the reverse of the normal margin of error formula, Z times sigma over E all squared. So if you notice here, it really doesn't matter whether we use the positive or the negative version for E down here. I'm just going to use the positive version just because there's less room for error there. No pun intended there. So actually, yes, I intend the pun. We'll go with that. 2.575 times 0.025. So that's our, actually, whoops, almost made a mistake there. I don't need my error on top, I need my deviation on top. So my deviation is 0.068 squared. And then I have my margin of error that I want down below. So let's figure out this here. Turn my calculator on. 2.575 times 0.068 divided by 0.025 all squared. We get about 49.056. So 49.056 0.056. So if he wants to be extra safe, he'd have to survey 50 quarters, find their weight, average them in order for his survey to be within the 99% confident range. So this would be the number of quarters. Again, we'd round up just to be certain, but this would be the amount of quarters he'd need to survey in order for his machine to be within plus or minus 0.25 grams 99% of the time. So again, will people still use slugs and will they work occasionally? Yes. But if he wants to narrow his machine down to this amount of margin of error, he's going to need to survey 50 quarters to get his point estimate and then run the data that we've just been doing here to get the range of values to set his machines to. So that's it for this video. Again, it all boils down to point estimate plus or minus margin of error. It's just the point estimate is going to change depending on what we're averaging or what we're testing the proportion of, and then the margin of error is going to change whether we're testing a proportion or an average. So as long as you keep that idea in mind, we should be good going forward. Hope the video helped you out. Have a good day.